So, obviously, if you want to read a little blurb about McLaurin, he's over there. What I want you to do is just read those two boxes, kind of skim through those two boxes to yourself for a minute. So, Theorem 1014 and then the definition. Okay. Should not be new things. We're just adding the word series instead of polynomial. Okay. Um, so, and we're also putting in there the thing called power series. Okay. So, a power series, remember, has this form. Okay. Which looks pretty much like a Taylor, right? This little, except that this is a coefficient. Is just how do we create that coefficient? Okay. So to create the coefficient, we use, or the a sub nth term, we basically use this little formula, which is really saying the function evaluated at the nth derivative of c over n factorial. That's how we get that number in front. And then we can create this. And this piece right here is typically what we call the general term. Okay. And really that was the official theorem of a convergent power series. Okay. The definition is basically, it's the same format, right? And this is what we've been doing the whole time. We just go out to the nth. We call that a Taylor series. This again is the sigma notation with the general term in it. So see how this thing here, this part here and this part here are identical, except they put a sigma notation in front of it. Okay. And I was actually reading in my little Facebook group over break, they very rarely ask you to write it with the sigma notation anymore. It's just they want you to make, sometimes you have to write the general term at the end. Okay. And we'll practice that a little bit the next couple of days. And then, as always, if c is equal to 0, it's more specifically a Maclaurin series, but we know Taylor at c equals 0 is Maclaurin. We've been working on that. All right, so we're supposed to find the Maclaurin series. They actually do want it in summation form in this particular problem for the following functions, and then find the interval of convergence for the series as well. So there's a lot going on. This is going to take us a little bit. It's going to be kind of tedious. Okay. We are going to start with, just because it's been a week and a half probably since we've talked about this, let's talk about just how to recreate this, even though in theory we should have cosine x memorized. Okay, it should be one of the things that we have memorized. I think there was a chart earlier, wasn't there? Wasn't there a chart in the ones you were supposed to watch at the end of break last week? Maybe. My chart should be in there somewhere, shouldn't it? There wasn't a chart? Did I lose the chart? Maybe it's at the end of this one. I think maybe it's in this lesson. Is it in this lesson? Flip. It's on the next page. Okay, so we're going to talk about that chart more specifically and what you actually need to know from there. Okay, but we're going to recreate. Okay, because we know if we don't have the chart memorized, we can always recreate it. It's time consuming, but we can do it. Okay, because we are Maclaurin, what's your C value? 0. Good. Okay, so I am going to make my little table. Okay, and I'm going to put it out in the left-hand column because I do not have a lot of space. I want the function, or f, and its derivative there, and then we're going to evaluate for c equals 0. They did not really give us an ending point, but you typically, if they don't, in an entire series, you want to show 3 to 4 terms plus your general term, your nth term. Okay, so I am going to start with my function is equal to cosine x. Okay, so what is f prime equal to? Negative sine x. Good. All right, then what's f double prime equal to? Good. And f triple prime is equal to sine x. Now here's the problem. We know that when we evaluate for 0, some of them are going to drop out, right? So I probably need to I'm going to go a little bit further than just the first 3 derivatives, because I know that with sine and cosine, some of my terms are zeros. So I'm going to go to like the 6th derivative, it looks like. So 4th derivative, I'm going to write it like that. What's the derivative of sine? Cosine x, good. 5th derivative is going to be negative sine x, and then the 6th derivative is going to be good. If you need it, you can always sketch your little unit circle, right? That's about as much of it as we need, is that coordinate. All right, and literally I am plugging in the 0. So cosine of 0 is equal to what? 1. Good. What is negative sine of 0 equal to? Good. Negative cosine of 0 is equal to? Good. Sine of 0 is equal to? 0, right? And then cosine of 0, you already told me 1. Negative sine of 0, you told me 0. And negative cosine of 0, you told me negative 1. Give you a minute to catch up. Okay, if it helps you, all right, when you're writing and expanding this out, okay, what I sometimes like to do is I will just put my variables in there right after my values in my table. I know the first one is like an x to the 0 power, so it doesn't get anything on it. This would be x. This is going to be x squared, x cubed, x to the 4th, x to the 5th, x to the 6th. If that helps you, okay, it's not necessary. It's not something other people do. It's something that Mrs. Ballard does to help herself out. Okay. All right. Now I'm going to write my expansion for cosine x. So this is my Maclaurin series. So I start with 1 plus. Now, my second term is going to be, I'm not going to write my 0 terms. We're beyond that. Okay, so I'm going to get rid of the 0. I'm going to go, so I'm not really writing plus. I should be writing minus x squared, right? Because that's my x minus c part. My coefficient was the negative 1 over 2 factorial. And then my next one, it looks like it's a plus x to the 4th over 4 factorial. And the next one is minus x to the 6th over 6 factorial. Plus dot, 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 plus. And then I'm going to write my sigma notation, my summation form, or my general term at the end. I'm going to start with n equals 0 to infinity. And then we're going to see if we can create that. I think we worked a little tiny bit, not much, but we did try to create some patterns in general terms in the very first lesson or two of Unit 10. Okay, so the first thing, what do we know is happening with the signs? They're alternating, okay? So the way we write alternating, or the way we recognize alternating, is we have negative 1 to some power, right? So I'm going to make sure that that's in there. Negative 1. And it's either to the n power or the n plus 1 power, and it depends on where you start, okay? In this case, I said, hey, let's start with 0. So this is my 0 term, right? Right there's my 0 term. So when I put negative 1 to the 0, I would just get a 1, right? Or nothing, right? It would be a positive 1. So that gives me a positive. And if I think about it, when I put in my second term, my n equals 2, when I square the negative 1, it would stay positive. Or sorry, it would be, I'm sorry, this is the first term. This is the 1 term. So it would stay, whatchamacallit, it would go negative. And then technically this is the second term. It would go positive, third term, and so on. Okay. All right, then I need to figure out what's going on with, so this is my first term, second term, third term. I'm trying to look at my pattern based on my term number. Okay, so this is just your term numbers. It's not really part of the equation. Okay, I'm just trying to help us recognize the pattern. All right, I need to figure out how to create my exponents on my x's from my term number. What does it look like is happening comparing my term numbers to my exponents? What's going on? What's going on every time? Okay, n plus 1. Let's try that. So if I did n plus 1, that would mean I'd have 1 plus 1 is 2. 1 plus 2 is 3. Did that work? 2n. Okay, so if I tried that. So if I did 2n, 2n would be 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6. Does everybody see 2n going on there? Okay, so we're going to use 2n. But it's okay to get it wrong the first time. But did you see how I tested it? Okay, we guessed n plus 1 first. I'm going to make sure that works for all of them. Okay, it didn't work. I'm going to move on to the next thing. Okay, the worst that happens is I make a mistake and my brain grows a little bit and I move on to the next thing. Okay. All right, look at the denominator. What should I write in the denominator? Is it any different than the exponents? Is it just n? Yeah, 2n. It's going to be 2n again. It's the same pattern, right? And then with the, it's not an exclamation point. We call that factorial, remember? 2n factorial. Okay. So that took care of the first sentence, right? Find the Maclaurin series in summation form for the following function. Okay, perfect. We got cosine x. We expanded it. That's the Maclaurin series. We got the summation thing at the end. Unfortunately, there's another sentence there, so we have to take care of that other sentence. Okay. All right, so we're going to find the interval of convergence for each series as well. Okay, so it's a good review from what we were doing before break, which is probably why it's good to just quiz these sections together. Remember, to find the interval of convergence, we need to perform a ratio test. So that's what we're going to do. And we're going to use this general term that we created right here to perform that ratio test on. Okay. When we are doing the ratio test, the first thing you do is take the absolute value. So my negative 1 to the n, I'm just going to ignore it. And I'm just going to do the ratio test on the other two parts. Okay. So we're going to do a ratio test. I'm going to write that little note in there. You don't have to write it, but at least taking notes, that helps a little bit. All right, so I've got the limit as n, not x. I wrote my m way too much. Let's start over. Limit as n approaches infinity. What do I have to plug in for the ratio test? N plus 1, right? So I'm going to go x to the 2 times n plus 1 over 2 times n plus 1 factorial. And then remember, we divide by the original or we multiply by the reciprocal. So we get 2n factorial over x to the 2n. Okay, because of my spacing, I'm going to keep going to the right, okay, because I have lots of room to the right. You have a sticky note if you need it, okay? All right, so I am going to make an attempt, before I make an attempt, I'm going to go ahead and distribute that too, because I'm not really sure what it's doing with things right now, so I'm going to start there. So the limit as n approaches infinity of x to the 2n plus 2 over 2n plus 2 factorial times 2n factorial over x to the 2n. Okay, I'm going to start taking some things apart and expanding some factorials and see what happens with it. So the limit as n approaches infinity of, remember when I have addition like that, I can take it apart with multiplication. So x squared. Actually, literally just taught that property first period this morning, only the backwards of it. The two bases the same, we add the exponents. All right. Then on this denominator, I'm going to expand. So I'm going to start with 2n plus 2 What comes before 2n plus 2? 2n plus what? Plus 1. And then before that, we would just get 2n, right? Because if I subtract another one, it would be 2n plus 0. And then I'm just going to leave it 2n factorial over x to the 2n. You can put them together under one fraction. That's fine either way. That's a 2n, even though it looks super tiny and scribbled. Okay, what cancels? X to the 2n, what else? 2n factorial, perfect. All right, so I'm going to write down what I have left, okay? And I know I'm using a lot of steps for this one, but I'm making sure we're understanding every single little part. So limit as n approaches infinity. I'm going to write it as x squared times 1 over 2n plus 2 times 2n plus 1. Okay, so I am going to substitute the infinity in, right? So we have x squared over 1 over, basically I get infinity times infinity, right? What's 1 over infinity? 0. So that would just be 0, wouldn't it? Okay, do you guys have your orange sheets up? Pull your orange sheets up. We're going to need them right now. Okay, look at your ratio test. What just happened with that series? Good. Why does it converge absolutely? Good. Okay, so because it's less than 1, it just converged absolutely, which means that my interval of convergence is everything. Okay, so we're going to summarize that and write that down underneath here. So therefore, it converges absolutely, and the interval of convergence is between negative infinity and infinity. All right. Not short today, are they? They never are in here. The good news is we've only got one section left in chapter 10 or in unit 10. Then we get to go back and do 9. 9's nicer. It'll feel like we're in an AB again when we do 9. All right, we good with that part of example 1? Okay, so we do kind of something similar here. Different function. And we will so we're going to look at the different function. But again, I'm going to follow the same process I did before. Okay. With a rational, we're probably not going to see it drop terms out like we do with a sine or a cosine. Okay, so I'm only going to go to like the fourth derivative on this. Okay, because I do have to figure out what my pattern is and be able to write my general term and all of that fun stuff. Okay, so I'm going to again choose to try to squeeze in my function and its derivatives out here. Notice I'm leaving a lot of space on the left and not nearly as much on the right. It says it's Maclaurin again, so what's my C value? 0 again. Okay. All right, my original function f is 1 over 1 minus x, which remember I could rewrite as 1 minus x to the negative 1 power. Okay, so my second derivative, the 1 minus x to the negative 1 is better for the derivative. The way I have it written the first time is better for plugging in the c equals 0 part. Okay, so I really kind of want both of them. All right, so I'm going to go through and I'm going to do both of them on everything, but I'm going to use this piece of it, which is going to end up in the front for all my derivative pieces. Okay, so remember derivative, we take the number at the exponent and we bring it to the front. And then we subtract 1 off the exponent. So what's going to be my new exponent? And then what do I have to be careful of? I'll give you a hint. It's orange. Yeah, we got a chain rule going, right? Isn't there a chain sitting inside of here? What are we going to get off the chain? Do we really need to write down our chain rule to add a negative 1 in front? So what am I going to do to the sign every time? I'm going to change it, right? So it's going to change to a positive because of the chain rule. Okay, that was what happened with our chain. Okay. All right. And then if I'm going to write that pretty, right? So it would be 1 over 1 minus x squared. And I'm sorry, I'm really squishing it in there. I can make it bigger for you guys to read it up there. Okay, so the derivative piece I'm going to get off the first part of the equation, and I'll use the second part when I plug in the 0. So I'm going to go f double prime equals. All right, my negative 2 is going to come to the front. 1 minus x, what's my new exponent? Negative 3, what's going to happen to my coefficient? Positive y, chain rule, okay? And then if I'm going to write this pretty, it would be 2 over 1 minus x to the third. All right, and I said I was going to go 4 derivatives, so I make sure I establish enough of a pattern to be able to create my nth term or my series, okay, my general term of my series. All right, so the negative 3 is going to come to the front. What's 2 times negative 3? Negative 6, 1 minus x to the negative 4. What's going to happen to the coefficient? Positive y. Chain rule, good. So 6 over 1 minus x to the fourth. All right, finally, fourth derivative. So 6 times negative 4 would be negative 24. 1 minus x to the negative 5. And then what do I have to do in front? Plus for the chain rule. So we've got 24 over 1 minus x to the fifth. All right. Our goal now is to figure out all of our little coefficients in front. That's where the c equals 0 part comes in. I am mostly going to plug into that part of the column right there. Okay, we're going to mostly plug into here. Okay, except for this first one, it's written in the front. Okay, so I get 1 over 1 minus 0. What's that? 1. Good. We get 1 over 1 minus 0 squared. What's that? So I put 0 in here. So I get 1 minus 0. What's that? 1. 1 squared is, and then 1 over 1 is 1. Good. In fact, what are all the denominators going to end up being? They're all going to be 1. It's all going to have the same pattern. So aren't I just going to get the numerator coefficient on all of them? So this would be 2, 6, and 24. What did I do wrong? Something went wrong somewhere. I lost my signs in here somewhere. I'm going to put that down there. We messed up the sign somewhere. I bring the negative to the front. We've got the chain rule. No, it seems to be. But I had a negative there last year. What did I do wrong? Did I miss the chain rule? Maybe I missed the chain rule last year. I think I did. So I see a negative. Yeah, I don't think I did the chain rule last year like I was supposed to. Okay, we're good, I think. So let's go ahead. This is again, it's no variable. It would be x squared, x cubed, x to the fourth. Okay. I still feel like I have a sign mistake in there somewhere. Let me pull up where I stole these from. I just want to make sure I'm thinking about this the right way. So I don't want to totally mess this up and have to go back in and figure it out again. So let me pull them up. The official answer key. This. And that. And practice. Gives you a mental break though, right? Oh, that might make it a solution. Solutions. 14. Okay. Good news. I'm right this year. I was wrong last year. Good thing I didn't video it last year. Okay. So we're going to go ahead and expand that out then. Okay. So we've got, let's write our series out. So the 1 over 1 minus x equals 1 plus x to the first over 1 factorial plus 2x squared over 2 factorial plus 6x cubed over 3 factorial plus 24x to the fourth over 4 factorial dot dot dot. I'm going to take a couple of lines to get that sigma notation in there. Because I want to see if I can figure out the pattern that's going on here. Or see if I can simplify that in some way. What is 2 factorial? 2, so let's see. That looks like this crosses. What's 3 factorial? Ooh, what's 4 factorial? Ooh, so what happened every time? Canceled. Okay, so now let's write the new expansion. So it'll be 1 plus x squared plus x cubed plus x to the fourth plus dot 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 plus, I'm going to go 0 to infinity. So if this is, I'm going to put my term numbers in here in the box just so you can see it. So this is term 0, term 1, term 2, term 3, term 4. So x to the what? So the only thing that's changing is my exponent, right? Just x to the n. Good. Okay. Looking back at what I did last year. So there's a couple of ways that we could look at it from here. Okay. Why don't we just do, because we're used to doing the ratio test, let's just do a ratio test on it and see what happens. Okay. So let's pull out our ratio test. Okay, so ratio test says that we take and we put in, whatchamacallit, n plus 1, right? So we have the absolute value of x to the n plus 1 over x to the n. And we don't have to do the flip and multiply thing. We don't have a fraction this time like we normally do. Okay. What's wrong? Oh, yes, thank you. I totally lost my limit. Limit as n approaches infinity. That's important, isn't it? All right. So we've got the limit as n approaches infinity of x to the n times x over x to the n. Okay, what happens with my x to the n's? They cancel, good. Okay. And we just have the limit as n approaches infinity for the absolute value of x. All right. So there's nowhere to put in the n, right? We know our series, our limit has to be the absolute value of x. To force it to converge, it has to be less than what? 1. Which means that the interval we're looking at is between -1 and 1. But remember how we had to check the endpoints thing? So we need to do some endpoint checking to determine if we have equals to or not. Okay. So this is good practice of that. We're not going to do the last example today. We will say, I think this is enough for today, don't you? All right. So we're going to save that one for tomorrow. So we're going to do 4x equals -1. And we're going to put it in n equals 0 to infinity. And we're shoving it into this guy right here, right? So it would be -1 to the n. Okay, so I want to look at, that would be, really, if I think about that series, right? Think about what's going on. I'm not sure. I think nth term would probably work on it, wouldn't it? Limit as n approaches infinity, if I did nth term. We would have -1 to the n. I put infinity in there. -1 to the infinity is going to just be something that is not equal to 0. That's as much as we need to know, right? It's either going to be -1 or +1 or -1. It's going to alternate back and forth, isn't it? So that one for sure is still open because it diverges, right? On that endpoint. All right, let's try our other endpoint. So 4x equal to 1 n equals 0 to infinity of 1 to the n. I could probably use nth term again, couldn't I? And we've got the limit as n approaches infinity of 1 to the n. So again, it's going to be like 1 to infinity, which does not equal 0. So what happens? I heard Stephanie say it. Diverges again, right? So our interval stays open on both ends. All right, we're going to call it good right there. And we will finish up that last one.